Hey everyone, and welcome to Dr. Abu RTN Academy channel. Today we are going to discuss part 1 of Seminar 9 for the University of Debrecen and the Biostatistics subject. In this seminar we are going to discuss the chi test. It looks like X but it's called chi, okay? Chi test, okay? Which is X square, called chi. Chi test, screening tests, the specificity, sensitivity, and positive and negative predictive values. Also, we'll study the retrospective study or case control study, and we are going to discuss also the odds ratio. Okay, the fourth point here will be the prospective study. So we'll have the retrospective. Retro means something happened in the past and we are trying to capture it. Pro means we are expecting or predicting something which is going to happen. Okay, so we're going to discuss the retrospective, the prospective, and the analysis of survivor curves. Okay, like Kaplan-Meier curve and the average survivor time. And along with these studies, we'll illustrate the ideas of each point by examples. Okay. So we'll start with this example on a statistics test, and this example it says the U.S. Veterans Administration conducted a healthy survey of 1,783 veterans to investigate the correlation between sleep problems and the previous military service in Vietnam. So they want to see if there is any correlation between the people who had some military services in the war in Vietnam between USA and Vietnam and their sleeping problems, because there was some saying or some rumors saying that there is a relation between the sleeping problems which American soldiers have who have already served in the military war with Vietnam. Okay, the contingency table below summarizes the results. So we have here the service in Vietnam. Okay, the service in Vietnam, whether the soldiers has been served there, yes or no. So if the soldier has served in Vietnam, yes, and he has sleeping problem, yes, so the number in our sample is 173, okay? And for the soldier who has served in Vietnam and they don't have sleeping problem, their number is 599. So the x-axis here, this yes and no, is for the service in Vietnam. Yes, they have served in Vietnam, or no, they haven't served in Vietnam. The vertical column, which y-axis, sleep problem. Yes, they have a sleeping problem, or they don't have a sleeping problem. So in this problem, we have two dimensions, x and y. It's called two-dimensional problem. So the question here, whether there is a correlation or no. They want to investigate whether there is a correlation between the sleeping problem and the previous military service or no. Okay. So here the question, can we conclude that at level of significance of 5%, so here we have alpha 5% or 0.05, that sleeping problem are independent of a previous military service in Vietnam or no? So this will be our null hypothesis. Null hypothesis means our expected hypothesis, that we are assuming that this is true. It will happen that there is a relation, that there is no relation between the sleeping problems and the previous military service. So both are independent. So there is no relation between them. So our H note here, we will assume that there is no relation. They are independent. So if this hypothesis H note or H null accepted that they are independent, there is no relation. So we'll accept our H note or H null, okay? And the say which is saying that they are dependent and there is a relation, it would be wrong, okay? But if we rejected our H null or H note, okay, which says that they are independent, this means that they are dependent, okay? So in the solution here, the null hypothesis, H note, we will assume here that this is our assumption, which we believe it is true. Okay, so sleeping problem and the military services in Vietnam, they are independent. The same thing which we have here. So they are independent. So if we accept this hypothesis, this means that there is no relation between them. They are independent. Okay. If we reject that, this means that we will have a relation between them. As we have said earlier, that if we have H naught and it is rejected means that we are not in agreement with it. But maybe a small part of it is still true. We reject it, but there is a small part which is true. Okay, it is called alpha. Okay, so there is a possibility that there is some error there in our judgment. We said it is rejected, but there is still an error which it could be true or right. Okay, so this is called alpha. But if it is rejected, this means rejected, but still we have an error of small percentage. This is called type 1 error. Okay, type 1 in Latin, error. Okay, so it is error, but error of type 1. So the point here that assuming that null hypothesis is true, if we assume that this null hypothesis is true, they are independent. Okay, assuming that it's true, calculate the expected frequency in each cell. So now we have two dimensions, as I told you, we have X and Y, two-dimensional problem. Okay, we have to check the number of column and the number of rows. The number of column here, number of rows here, 1 and 2. The number of rows which has numbers, has values. Okay, and number of column also 1 column and 2. Okay, so we have to get N row, NR and NC. Okay, NR and NC. We will need NR and NC, the number of rows and number of columns, when we come to calculate the degree of freedom. Okay, DF. Degree of freedom in this case will be equal row, number of rows minus 1, times number of column minus 1. Okay, so in my case here, the number of rows equals 2, number of columns which has values equals 2. Okay, which has the given values. Okay, so what are these numbers called? This number called observed value. Okay, the observed reading, observed value. Okay, when I do the experiment, I count the number of people, because these are distinct category. Okay, so it's not a continuous, it has to be counted. So here, this number 173 is the frequency in this category. The frequency of the number of people under this category 599. Under this category was 160. Under other category 851. So this is the frequency of these people in these cells. So this value is called the observed value. Observed means the values which we have observed in our experiment. Okay, it is observed value. So we have two values. One of them will be the observed value, observed, which are these numbers. Okay, which has been given in the question, and the other one will be the expected values. Okay, so I have two values, one of them observed value and the other one is expected value. So I'll call them O and E. O noting for observed and E for expected. Okay, so now I have got one of these values, which is the observed value, has been given in the problem. But before coming to how to calculate the expected value, I need to understand something. So here I have two variables. One of them serves in Vietnam and the other one sleeping problem. Sleeping problem in the vertical axis and services is on the x-axis. So all what we'll do now, just we'll copy this table and we'll add some cells here, or just will extend some cells here and down here. This will be for the total. So here the total of this column, here the total of this column, here the total of this line, row, and this is the total of this row, and this is the overall total, okay, of rows and columns. For example, this is one service, okay? Service in Vietnam will give one notation for it. For example, Z, X, Y, A. So I'm giving here A, and I'm calling, if it is service in Vietnamese, he has served, it will be A1. If it is no, it will be A2, okay? Just for explanation purpose only, okay? So here it will be A1 and A2. And here sleep problem, yes, will be B1 and no will be B2. So if I'm looking at this value will be intersection of A1 with B1, A1 with B1, okay? The other one will be A1 with B2, and here will be A2 with B1, A2 with B2, okay? So concentrate with me please here in this area, because we need now to go and see how to calculate the expected value. So the expected value in any cell, so if we want to calculate the expected value for A1, B1, this cell, A1, B1. So how can I calculate it? I'll take the value in this A1, what is A1? This A1 column, okay? The column, yes, all this is A1, okay? But I'll not take it from this table, because I'm supposed to have a table with the total year, which we'll find in the next table now. So I have to use this table. So this table I have here, this is the value, observation value 173, and here 173. Forget about the one which is highlighted in yellow. Okay, so observation also, this is the observation. All this table is observation values, okay? So here, this one is 599 and 173. Total is 772. These are the sum of these two numbers, okay? The same thing here, I have an A2. This is the observed number, and this is the other observed number, and this is the total, 1011. So adding up 173 plus 160 equals 333. 599 plus 851 equals 1450. 720, the total of the column plus the total of the other column, will give me 1783, which is the same number which he has given you. So our calculation is correct. So how to calculate the observation value? Observation value here, this is A1 and this B1, so this is A1, B1. How to calculate A1, B1? A1, B1 means the number in A1, the numbers for A1 times the number of B1, because this we'll consider just like A1 and A1 and B1, okay? So the number in A1 times the number in B1 divided the number of N total, okay? So how we can calculate it? Here, this is A1, column A1, and this is column, and this is row B1, okay? So what is the value for A1, the total of A1? A1 is here. The total is 772. Okay, so this is the total, the number in A1. This cell is A1, B1. It is not A1. And this one, A1, B2. So it is not A1. This is the A1, okay? Because this column called A1. So the total is A1. Here, A1, B1, A1, B2. So here, the observed value will be equal. Our cell is, I want to calculate A1, B1, A1, B1. So it will be the number in A1 times the number, so the number in B1 divided the number in the total number, okay? So what is the number in A1? A1, this is the number 772. Times the number of B1. What is B1? This is B1, 333. Divided in total, what is N total? This is N1, N of A1, this N of A2, this is N, 1783, okay? So by calculating, I get 144.2, which this is the observed value for the cell A1, B1. This is A1, so it will be 144.2. The same thing we can do for any other cell. Let us take cell, for example, A2, B2, this cell. Here A2, here, and here B2, okay? So we'll take cell A2, B2. A2, B2 equals N A2 times N B2 divided total number, which is N. So what is N A2? Okay, the number of A2 is here 1011. In B2, the total number is 1400 times 1415 divided in, which is 1783. So the answer will be 822.2, okay, which is this number, 822.2. And in the same way, we can calculate A1, B1. We can calculate A1, B2, and so on, okay? This one and the other, and the A2, B1 as well. In the same way. Then, by having all this calculation, we get something called observed value. But we don't need this observed value. What we are looking for, the difference between the observed value and the expected value. So after we got the observed value from the table, and we calculated here in this table, we calculated the expected value. So what we'll see, we have something called the chi. Chi, it is not x. It is looks like x, but it is not x. Okay, so it is like x, but it's not a real x. It's called chi. Chi square equals what? Expected sum of expected value minus observed value, okay, square, divided the expected value, which is this one, okay? So here the sum of expected value minus observed value. So for every cell, I have to calculate it. So in the next page, we'll see the details of the calculation. So here, this is chi square, okay? Chi square equals sum of expected minus observed. Only the denominator is squared. Denominator is not covered in the square. So the point here will be the first one, 144, expected 144 minus 173 divided 144. Let us go and see. 144 here, and the observed is 173. So expected minus observed divided expected again. Okay, and the same thing for all the cells. Sum, so I have to have plus. So my answer is 12.48. Okay. If you remember in the graphs which we have taken the last times, we said that for every cell we have something called alpha. Alpha, this is the error percentage, okay? So the alpha in this area. If my number came inside this rejected area, this would be the rejected, because we are assuming that H null or H naught is true. This always, we are assuming H naught is true, and not always, usually, we are assuming H. So if it is within the rejected zones, then H naught will be rejected. H naught will be rejected. So I have to see the answer. For example, if I might calculated here alpha, critical, and we have alpha calculated. So let's see if the calculated is here, so it didn't come inside this zone, so it will be okay. So we can say that we are not rejecting the HNL, okay? But if the value came here inside this region, so it will be inside the rejection zone, so we have to reject H naught. And if we reject H naught, it will be type 1 error. So here we have chi square, and we have table from where we can get the critical chi square. So this is chi square, but based on my calculation, based on this table, okay? This is called calculated. Chi square calculated, okay? Or both squares. Chi square calculated. Now I have from this significance, so the degree of freedom equals the number of rows minus 1 times the number of columns minus 1. So this is 2 by 2 table. Let us see it. So here, how many rows I have? I have 2 rows. Someone will say I have 4 rows, 1, 2, 3, 4. No, we are looking at the rows which has observed values. This is the observed value, this one and this one, So how many rows? 2 rows. How many columns? 2 columns only. Okay, so we have R equals 2 and C equals 2. So R minus 1, it will be 1. C minus 1 equals 1. So 1 times 1 equals 1. Okay, so it will be 1 times 1 equals 1. Okay, so my degree of freedom is 1. And what is my significance level alpha? 5. So here it is 1 minus alpha. So I have to be very careful. 1 minus 0.05, which is 95%, or 0.95. Okay, so at this 1 minus alpha equal 95%, or 0.59, and degree of freedom 1, I got this value. So this value is, which is chi-square, so chi-square, but critical, not calculated. So if I assume here that the critical one is 3.8415, so this point will be 3.8415, and we start from here, start from 0, 1, 2, 3, we reach 3.415. So here this is the critical point. Anything more than this critical point from the right side, it will be in the rejection zone. If we have another one which is negative, anything more than but in negative sign, this one it will be inside it. Okay, or in general, if something value is less than the critical, so it will fall inside this one. Okay, like minus 3 and minus 4. If it's minus 4, it starts from 0, minus 1, minus 2, minus 3, minus 4 will be inside it. Okay, if this is minus 3. So here in our case, chi-square equals 3.84. So what about the calculated one? The calculated one, we just get it 12. So 0, 1, 2, 3, 4, here 3. So 12 will be very deep inside it. Okay, it will be very deep here. This is, for example, 12 point something. It doesn't matter where it is located, but it is inside the rejection zone. If it is inside the rejection zone, so I have to reject each node. So this means that since the calculated value of the test statistics is larger than the critical value, because this is 12 and this is 3, so it's larger, so it falls inside the rejection zone. So I have to reject the null hypothesis. So the null hypothesis is rejected. If the null hypothesis is rejected, means type 1 error. Okay, type 1 error. Okay, if we rejected the null hypothesis, so means that the alternative hypothesis is correct. What was the null hypothesis which we rejected? We assumed that the null hypothesis is sleeping and the military are independent. If we rejected this means that they are dependent. There is a correlation between them. Okay. The null hypothesis is rejected. The alternative hypothesis is accepted. It can't be assumed. So now it can't be assumed. We cannot, because we rejected this assumption. It cannot be assumed that the military surface is independent of a sleeping problem. Okay, so it may be dependent. Okay, I hope this example is clear. So now we knew how to calculate the chi-square, how to calculate the expected values, okay, here in this table, and then we subtract expected value minus observed value divided expected value after squaring the denominator in order to arrive to chi-square. Okay, and we knew also how we can get this expected values, that if, for example, I have this A1 and this is B1, so this cell is A1, B1. So how to calculate A1? So the sum of A1 means the column A1, the sum here, okay, of column A1, B1, the sum of B1. So this will be multiplied 772, the sum of this one, times, which is 772, times 333, okay, divided the overall n. So for each cell I have to do the same thing, okay. For example, the second cell here, A1, B2, A1, B2, So this one A1, B2, so it will be A1, I'll take the sum of A1, B2, I'll take the sum of B2, okay? So 772 times 1450 divided the overall, and so on. In this example, it is the same methodology, the same thing. We have the contingency table, okay, which is this table, okay, has all the numbers, okay, all the numbers of all the conditions which we have. I have two conditions here, okay, so one on the x-axis and one on the y-axis. The one on the y-axis, it will be for the disease, whether it is treated or cured or not cured, okay, cured or not cured, okay. And for on x-axis, I have three conditions. I have three protocols for antibiotics, okay. I'll call one of them A1, and second one I'll call it A2, and third one I'll call it A3, okay. And I have the reading for each one. So for the first antibiotic protocol, this one, okay, I have two conditions. The one who take this protocol, maybe they have been cured, or maybe they have not been cured, okay. The second protocol, maybe they have cured or not cured. Third protocol, cured or not cured. So this is called observed values, okay, or the observation table. So these are the reading which we have taken from the sampling, okay, the population which we have get a sample, and this is the readings or the actual counting for each category, because here this is discrete data, it is not continuous data. So every category has the number of the frequencies. So how many cured, we have the frequency of the cured people, okay. How many not cured, this is the frequency of not cured. The treated people for this protocol 1, this is the number. The second protocol A2, this is the number. Third protocol A3, this is the number of the people, and the intersections also are here, okay. So this is called the frequency for each category. So we put them into categories or classes, and for each class or each category we are putting the number of frequencies. So based on these observed values which we have here, okay, we have to calculate, have another table, similar table with the expected value. So first I have the observed value, and I need to calculate the expected values. So let us take the first cell as an example here, okay. This cell is the intersection between A1 and B1, okay. It is A1 with B1. So A1, as I told you, this is the way how we can memorize A1, B1. So I'll take the sum of A1, okay, which is called N A1 times N B1, divided the total number N. So what is the N A1? This is A1, okay, and this is N, the sum of A1, okay, it will be 13, times N B1, this is B1, so the N, the total number, because this is not, N B1 is 20, okay, times 20, divided N, total N, what is the total N? It is not A1 or B1, it is the N, the total, which is 35. It will be in the most bottom right column, okay. So if we calculate this one, we'll end up with 13 times 20 divided 35 equals 7.429, which is equal to 7.43, okay, which is this figure. So here, by having this calculation, we'll end up with the expected value for the first cell, and we have to repeat the same exercise for each and every cell. Just keep in mind, this is not, if this is A1 and this is B1, B2, A2, A3, okay, this is not A1, NA1, this is A1, B1, this cell is A1, B1, okay, so the cell which we can call NA1 is N of the total A1, so the column itself is N1, so the total of the column, this total of the column of A1, it will be A1, okay, so this is called NA1, the total number in the column A1. So if I said NA1 means the total number in the column A1. So A1 has this one, and this is the total. So we can take the total directly. B1, the same thing. B1, this is B1, okay? So this will be the total of B1. So let us take another example. Any other cell, for example, let's take A2, P2, A2, B2, B2. So this is A2 and this is B2. So it will be this cell, okay? Okay, so A2, B2, and we need to calculate the expected value, okay, to put it in A2, B2. Here, this is the observed values, and we need to put here the expected values. Expected value. Okay, so the example which we will be taking now is A2, B2, which will be A2, B2. This is our cell in the observed table, and here we have to get A2, B2, okay, and the expected table. As we said, expected value will be A2, B2, it will be N A2 times N B2 divided N total. N A2, the sum of the column A2, okay, the sum of the column A2 in the observed value, this is A2, so it will be 12 times N B2, B2, this is B2, it's not this value, not this value, it will be the total, okay, it's not this value, because this table, by the way, it is 3 by 2 or 2 by 3, okay, it is 2 rows and 3 columns. Okay, so sum of B2 will be 15 times 15 divided N total, which is 35, the overall N. So it is equal to 5.40. Okay, so just put it here. So we just take the values from this observation table, okay, and substitute them in the formulas for each cell, okay, and arrive to the expected value and put it in this expected value table, okay. So once we receive this table, we can start working on this, but it's better to, before that, to set what is our null hypothesis. So our null hypothesis in this example, he said, is the treatment type independent of disease outcome? So the type of a treatment, whatever treatment you have given, it has no relation, it is totally independent from the disease outcome, okay? Perform the test at the level of significant 1%. It is not 5% in this case, it is only 1%. So our null hypothesis will be disease outcome, the same question which he has asked here. This is our null hypothesis, which we assume it is right. It may not be right, but we assume it is right. This is the null hypothesis, or it should not, that we assume that the treatment or the disease outcome is independent on the type of antibiotic treatment. There is no relation between them. So if this one is accepted or not rejected, this means that they are independent. If we rejected this hypothesis, means they are dependent. So we assume the null hypothesis is true. The expected frequency are calculated in each table. This is the expected frequencies, okay? So here we have the observed frequencies for each cell. So here the frequency here is 11 people, 2 people, the total is 13. Here the frequency 6, 7, 3. This is the frequency of the observed. And here, these are the frequencies of the expected, okay? So this is the expected frequency for this cell, expected frequency. The expected could be decimals, with decimals, 6.2, 5.3, and so on. But the observed should be integer, whole number, because you cannot observe that one person is sick or one person is treated or cured or not cured or took the antibiotic. It has to be integer, whole number, the number of people, the head counts. But here, the calculated or expected values could be anything, okay? So after getting this one, we have to calculate the chi-square. We have to calculate chi-square. Chi-square equals expected value minus observed value divided expected, okay? Divided expected value. But here, this one has to be squared. and this has to be done for each cell. Okay, so the expected value here minus the observed value, which is this one, divided the same expected value. Again, the expected value for this cell minus the observed value, okay, divided the same expected value again. For the second cell, this value, expected value, minus the observed value, divided the same one, the expected value again, for each cell. So that's why we put here sum. So after we get this expected minus observed square divided E for one cell, okay, you have to say plus the next cell, plus the next cell, and so on. Okay, so it will be 7.43, which is the expected value here, okay, minus 11, okay, square divided 7.43, okay, which is the first value. So this is the first one. We have to say sum of all of them, but since we are expanding now, and put all the value plus the second cell. What is the second cell? Here it is 6.86 minus 6 square divided 6.86, the expected value again, plus the next one, and so on. All of them. I have here 1, 2, 3, 4, 5, 6 cells, so I have to put all the 6 cells plus each other until I reach the end. Then I get the sum of them. So as we can see here, the chi-square calculated, okay, is the sum of for all cells. You can see here for all cells, okay, the sum of x expected, okay, expected minus observed square divided expected, okay, this is the first value, plus the expected minus observed for the second one, the third one expected minus observed for the third one, and so on. Then we can get it. Okay, so expected minus observed square divided the expected, and so for each cell. So we got the value, which is 7.26. Okay, so this problem, it needs to be practiced more, so you will be fast in using the calculator and how to get the value within the shortest time in order to save time in the exam. Okay, so the calculated value is 7.26. Once we got the calculated value chi-square, we need to get chi-square critical. Always we get calculated and the critical. So we already got the calculated, which is 7.26. So what about the critical? Critical we have to get it from the table. So in order to get it from the chi-square table said that we need the degree of freedom and we need alpha. Sometimes you find the table 1 minus alpha, sometimes you will find alpha. So you have to be careful which one you are using. If it's 1 minus alpha, so alpha in our case will be 0.01, so it will be 1 minus 0.0, it will be 0.99. But in this case, the table says alpha only, it will be 0.01. Okay, so you have to be careful which one you are using. The tables of chi which we usually have is 1 minus alpha, okay? Like if you see this table before, which we have 1 minus alpha, okay? 1 minus alpha. This table also should be 1 minus alpha. So the alpha in our case is 0.01, okay? So 1 minus alpha minus 0.01 equals 0.99. So this would be our 1 minus alpha, 0.99. So what about the degree of freedom? We said before, the degree of freedom in such type of two-dimension x and y, it will be the number of columns minus 1 times the number of rows minus 1. So how many columns we have? Someone will say, okay, we have this number of columns 1, 2, 3, 4, and the number of columns 1, 2, 3, 4, 5. No, the number of rows and number of columns are those who has values. Values mean observed value or calculated value. So here, how many rows we have who has observed value? 1, 2 only. What about this one? This is the total. This is not observed value. Okay, so this one will not be counted. So the number of rows equals 2. What about the number of column? Only the number of column which has values. Okay, So it will be 1, 2, 3. What about this one? This is a total. It cannot be counted. So 3. So number of columns equals 3. So it will be R minus 1 times C minus 1. Number of rows minus 1 times the number of columns minus 1. So I have 3 by 2. It will be 2 by 1. Okay, so this minus 1 equals 2. Minus 1 equals 1. It will be 2 times 1 equals 2. Okay, so this will be my degree of freedom. So coming to this table, I have degree of freedom 2. I have 1 minus alpha, which is 0.99. So my answer will be 9.2103. So by putting it on the distribution graph here, we'll see that 0.9, the rejection start of the rejection zone, 9.2103, this area, the rejection zone. If the value which you have calculated falls inside this zone, so it will be rejected because it came within the rejection zone. But if it is outside the rejection zone, so it means that we cannot reject the hypothesis, the null hypothesis. So here the critical value start at 9.2103, okay, and our calculated value was 7.26. Of course 7 will become, if here 0 1 2 3 4, 7 will come before 9, so 7 will be here. So 7 did not enter into the rejection zone, so we cannot reject our H hypothesis. If we cannot reject H hypothesis, means it is valid. So what our H hypothesis was saying? Our H hypothesis was saying that the disease outcome is independent of the type of the antibiotic. They are independent. There is no so strong or so strong a relation between them. They are independent. Or we can say that they appear to be independent, because we cannot judge 100%, because we still have type 1 error and the type 2 error. In this case, it is not rejected. If it is not rejected, it will be type 2 error, okay? Because still there is a probability that some error, although we accept the hypothesis, it should not, because it is not rejected, means we accepted it. Not rejected means we accept. If we accept it, but there is a potential that some error are there, should be rejected. Some potential, even a small percentage. That's why you call type 2, okay? Type 2 error. So we still have type 2 error also here. So here we can say that since H naught or H, the null hypothesis is not rejected, so this statement is valid. Okay? Sorry. This statement is valid. Okay? So the disease outcome is independent from the type of the antibiotic. So here, since calculated value, okay, which is 7.26, it is smaller than the critical value of H naught critical value. Okay, the critical value, which is 9, so 7.6 is smaller than 9.2. It is H naught is not rejected. Treatment, this which means that the treatment is independent of the disease outcome. There doesn't appear to be a relation between the cure. There is no relation between the cure and, okay, between whether it's cured or not. The cure of cystis and the antibiotic used and the type of antibiotic. It seems there is no relation between them. They are independent, okay? You have to remember that we have done this calculation for the importance level of 1%, okay? If we change this importance level, or the significance level or level of significance from 1% to 5% or 10% or 7% or 3%, the result may be different, okay? It might be different. So in 1%, they are independent, but if we use 5%, it might be different and they became dependent. So it depends on the level of significance. So in this case, with the level of significance 1%, they are independent. They are independent. But note that a different conclusion would be reached at the level of significance of 5%. I hope this one is clear.